the test would be accumulative. It covers everything. And again, Monday, November 29th, 2 weeks from now, and then we are done with this class. All right, any questions about this before moving on to talk about one more item also? It seems we are finishing this semester. Let me also look at the activity while we are here. Look at the syllabus for the activity. Our activity is also coming to an end. This is the activity I'm looking at. And this is where we are, November 8th. This is you work on project. And the project report is due November 22nd. So this is where we are, November 15th. We are working on the project, and next week is project report is due. This is the week of Thanksgiving, but it is on Thursday. It doesn't affect us. But on November 22nd, it is on Monday or Tuesday or Wednesday, but no later than Wednesday at the regular, no later than Wednesday during the regular activity period. It is when it is due. Don't leave it for the last minute. Just this is open on Canvas on Monday, so you can just go ahead and submit your report on Monday or Tuesday, and you are done with this. All right, but it will be available. Canvas will close, I think, on Wednesday at 12 noon, which is the end of the activity period. After that, it is closed, so no acceptance afterwards. Make sure that you submit it before on Monday or Tuesday. It is open. Again, next week, November 22nd. That is when the report is due. All right. So this is also about the project. We are closing, we are ending all our work, it seems, in a week or two. All right. Any questions about? All right. If no questions, let's go to our class modules. Scroll down. This is where we are, November 15th. This is the heat transfer. This is the second document. We will discuss this one next week, but let me we have not finished the first document. So let's see where we left last week. We were here, we talked about heat transfer, one-dimensional heat transfer problems, direct formulation, simplest type of formulations. We talked about conduction, where heat transfers through a solid. Between a solid and a fluid, it is by convection. Again, from solid to fluid, it is by convection. We looked at the formulas. For conduction, it is by Fourier's law, negative Ka dt over dx. And for convection, it is by Newton's law of cooling. It is HATS minus TF. This is fluid temperature. This is surface temperature, area, convection heat transfer coefficient, H. So we said in finite element formulations for conduction problems, for conduction, we said it is given by this, Ka over L, 1 minus 1 minus 1, 1. Temperature vector at nodes I and I plus 1 and Qi plus 1. So this is the formula for one element for conduction. This Ka over L, 1 minus 1 minus 1, 1. This is our element stiffness matrix in the language of solid mechanics. But of course, it is in the language of heat transfer discipline, it is thermal conductance matrix. But since solid mechanics dominated the field of finite element methods, so it is element stiffness matrix, we call it, or thermal conductance matrix. It is UA 1 minus 1 minus 1, 1. And U is this U factor, which is K over L. K is conduction heat transfer coefficient. And for convection, very similar to this one, HA1 minus 1 minus 1, 1, temperature vector and heat flow vector. So this is the, for convection, this is our thermal conductance matrix. But for a convective element, again, we call it element stiffness matrix in solid mechanics. So the general formula in heat transfer, it is KT is equal to F. K is global conductance matrix, temperature vector, heat flow vector. Very similar to solid mechanics. In solid mechanics, we call it global stiffness matrix, displacement vector, and force vector. Here we call it heat flow vector. Again, we call it solid force vector. We solved one example problem, that interesting problem, the heat transfer through a ceiling. We said that this room was at 70 degrees and 15 degrees here, heat convected and conducted through the roof. We found the temperature distribution. We selected 4 elements and we found the temperature distribution. Now, today, let's finish this this document here by discussing more powerful method, variational method, very similar to solid mechanics. So everything follows the same analogy actually with solid mechanics. Do variational method, the more powerful method compared to direct formulation. So that's what we are going to do, derive very important formulas, solve the heat transfer problem actually by finite element methods, but with very powerful method of variational method. Let's start with this one. So today we will discuss this one and then look at one example problem in this piece and then another one later. This is one element, one-dimensional element, node 1, node 2, length L. Now, this node is at temperature T1, this temperature T2. So if we look at this element, temperature varies like this, linearly with this way that we are defining our temperature function. This is temperature function, N1, T1, N2, T2. Question for you, N1 represents what? N2 represents what?
Shape factor.
Shape functions, N represents shape functions here. So this one, for one-dimensional problems, this is N. We said 1 minus x over L, x over L. So these are shape functions here. And T1, T2 are temperatures. So this function is actually approximation function, which or interpolation function, sometimes it's called also. As you see, it is interpolating the temperature anywhere along this element by this function. Oh, simple interpretation we can see here by a linear function. Sometimes we have more advanced types of shape function, which it is not just linear, it can be a quadratic like this, and so on. So this one, it is a simpler case, N1, T1, N2, T2 is our temperature function. N is shape functions given by this temperature. T1, T2 are in this vector form we represented. So T is NT. T is NT, where N is this and T is this. Now, defining a temperature gradient matrix G. This is the definition. We define G to be derivative of this T with respect to X. So this T with respect to X, we call it temperature gradient. So temperature derivative of this with respect to X is what? Derivative, this is constant, this is a nodal temperature. So N1, this is N1 with respect to X, derivative of this with respect to X It is negative 1 over L, as you see here. And derivative of this with respect to x is 1 over L. So this derivative of n1 with respect to x and n2 with respect to x, we show it by a B matrix. Everything we call it by a matrix. So this is B matrix. So B is derivative of n1 with respect to x, derivative of n2 with respect to x. Which is derivative of this is negative 1 over L, derivative of this one, and derivative of n2 with respect to x, this is n2, so it is 1 over L. So this is our B matrix for one-dimensional line elements. Now, by Fourier's law, Q is K dt over dx. Remember, there was an area here also. But this area we divided by this, call it a new term, call it heat flux. So Qx is actually, I wrote it as a note here. This is heat flux. This is heat per unit area, because this is the original formula that we had. Remember here, Fourier's law, we have K area here, times dt over dx. This is our heat flow, rate of heat flow. If we divided this one by area, bring this area here, that would be heat flux, heat per unit area. That's where we have it, we have here. So this one doesn't have that area, and it is called heat flux. dt over dx. Now dt over dx, we said that it is what? dt over dx is g. So we can write it as negative k times g here. This negative k, so this is this one, negative k times g. Negative k, this is a material property. Remember, materials, we put it in, like FEMAP opens a window for you and you enter all the material properties. So it goes to a material property matrix, call it D, just to make it general. So our heat flux Q is negative D, call it D, times this G. That is the heat flux. All right, look at an example problem. This is an element, node I, node J. Suppose this is at temperature 120 degrees centigrade. This one is at 90 degrees centigrade. Temperature varies linearly like this over this element. This is our origin here. So this node I is at 1.5 centimeter, this is at 6 centimeter, and this is the length of this element. The question is, what is the temperature at 4 centimeter from the origin? This is the origin, this 1.5. So 4 centimeter, let's say here from the origin, we want to find the temperature. Basically, we want to interpolate. And what is the temperature gradient within the element? Temperature gradient, remember, we showed it by G. That's what we want to find. To answer part A of the problem, well, just use this formula. We said that temperature varies like this, and N1 T1, N2 T2. N1 is this shape function. N2 is x over L. This is Ti over and Ti and Tj. All right, so here we need this lowercase x. What is this? Well, it is 4 centimeter from the origin. So from the origin is 4 centimeter, but this x here, as you see, this is local coordinate system. This is this lowercase x. It is from here. So from here, it would be 4 centimeter minus 1.5. This lowercase x is this. And that's it, plug the number. Length of this element, it is this length 6 minus 1.5, it is 4.5. Plug it into this 1 minus x over L. This is this one, x over L times Ti, which is 120. X is 2.5. Length and 90 Tj, it is 90. We get 103.3 degrees centigrade. This is the temperature at 4 centimeter from the, what we wanted to find, 4 centimeter from the origin. Part B, Temperature gradient. Temperature gradient, this was a new definition, remember, defining temperature gradient, G. G is this one, which is our B matrix, which is negative 1 over L, 1 over L times this temperature vector. This is our G. Okay, so here temperature gradient is simply dt over dx, which is negative Ti over L, Tj over L. Plug the numbers for Ti and Tj and L. We get this. Negative 6.67 degrees centigrade per centimeter. That's the answer to this question. Just one question for you before we leave this topic and talk about variational method. One, what does this negative mean? Remember, this was temperature gradient. And for temperature gradient, we got negative 6.67. What does this negative mean? Anyone?
It means that from node 1 to node 2, the temperature is decreasing as x increases.
Very good, you're right. This is temperature at node I and at node J. Slope is negative, dt over dj, or temperature gradient is simply slope of this line. So it is decreasing, so it is negative. All right, that was all our discussion in this part. Any questions before moving on? All right, no questions. So let's continue with the more powerful method. We are going to actually solve the heat transfer problem very generally today. And then apply it to 1D. And then next week we will do it to 2D. 1D are always very similar. The procedure is very similar to what we did in solid mechanics. So it is actually very, very similar in many respects. In solid mechanics, we used minimum potential energy formulation, which was a variational method. But the variational method, it was in solid mechanics more specifically, it is minimum potential energy. The same variational method, very similar to this one. Remember, in solid mechanics, we started with this one, so we will follow very closely in what we did before. So I move a little bit faster because you know the procedure. Pi h is our functional. It is a function of functions or potential function for heat transfer. In solid mechanics, we call it pi p. In heat transfer, we call it pi h. U represents stored thermal energy. This is U. Omega Q, this is energy due to heat source. Heat sources here. It's like body forces in solid mechanics. Omega Q, this is heat energy due to heat from the surface, due to conduction, heat transfer. Heat from the surface due to conduction. Omega H, energy due to convection from the surface. So these two actually represent like surface forces or traction. These two are like surface traction, body forces. Or this would be energy due to internal heat source. This is energy due to heat transfer, due to conduction from the surface, due to convection from the surface. Today we are going to make substitutions here, manipulate with them, minimize this one with respect to temperature, and derive very important formulas, which is very general in solid mechanics. I'm sorry, in heat transfer problems. But again, very similar to solid mechanics, more or less the same pattern. This is our functional, which is a function of functions. Consists of U. U is stored thermal energy. It is given by this 1/2 K dt over dx to power 2 dV. Now this is conduction heat transfer coefficient. This temperature gradient, remember we call it G. So this is this one, U. Omega Q, energy due to internal heat source. If you have some heat source at a node or from the surface, would be this one. So this one, like body forces distributed over the volume, it is given by this. It is negative QT times dV. Q is the heat source, heat per unit volume. Heat per unit volume times volume, it is heat times temperature. It gives the energy due to internal heat source. Omega lowercase q, this one, it is given by this. Q, this is heat flux, heat per unit area conducted from the surface, like surface forces in solid mechanics. Force, temperature, heat per unit area times area is heat times temperature. It is energy due to heat conducted from the surface. Very similar to this one. It is omega H, energy due to convection, heat transfer. It is given by this, 1/2 H T minus T infinity to power 2 ds. H is convection heat transfer coefficient. So now make some substitution, put everything in pi H here. That would be what? This is U, omega Q, and omega H. Now, instead of U, I use this one. This is what here it is. dt over dx is G. So this is G to power 2, which is G transpose dG. dV integrated over volume, this is our U. Omega Q, make this substitution, we said it is TQ dV. It is this one. It is TQ or Q, T dV. Put this T in front, but T is NT. We can write it as T transpose N transpose Q dV. Very similar to this one, it is for the conduction, energy due to conduction from the surface. S is surface, analogous to surface forces, and this one due to convection, omega sub H. These two, this is due to conduction, this is due to convection. Again, instead of in this formula, this is this one. Instead of T, use, remember here we said T is NT. T is NT, so this is this one. Bring T in front, so it is T transpose N transpose minus T infinity to power 2. A little bit more manipulation with this one. G, remember we said it is BT. So G transpose of this is T transpose B transpose. So this is what we see here, T transpose B transpose. But since it is constant, it's at nodal temperatures, it comes out. And the same for BT for G, we put it here. And the same here for in the second one, just this one comes out. These are nodal temperatures, comes out. These are shape functions, so it stays inside the integral sign. The same again, this one, for this one, this comes out. This stays here due to conduction from the surface. And this is this last term, but remember we have to raise it to power 2. So this is first term to power 2, second term to power 2, and then twice first term times the second term. It is here. This is twice the first term times here. I put a note here that it is the same, NT or T transpose, N transpose, it is the same. Now, this one, we have to minimize this with respect to temperature. Minimizing this with respect to temperature is this one. The derivative of this, so this one out, so it would be B transpose D. This is this one, B transpose D, dV. This stays here. Derivative of this with respect to time, this one out, so this remains. This is this one. Derivative of this with respect to T, this one out, so this is here. And derivative of this with respect to T, this is T infinity, so this would be 0. This would be the remaining terms, these two terms remain here actually. This H, this term for this, and this would be from here, this one remains, and it is equal to, put it equal to 0, we get this one. This is the very important formula. I highlighted these items also for you. From here, we get this one. You see there is this t here and t here. Factor this out. So this term, it is here, integral of b transpose db. And this term, it is here, times t is equal to this term plus this term plus this term, take them to the other side. Show them by f sub q, this one, f sub q, this one, f sub lowercase q, and this one by f sub h. Whenever you see h, it's due to convection from the surface, as you see here. So from here, we get this one. This, what you see here in this bracket, something multiplied by temperature vector is equal to some F. This is the heat flow vector, F sub capital Q, this one for this lowercase q, and this one for this. This is always what we like to see. Remember, in solid mechanics also, something times T is equal to F. This something is called our element stiffness matrix or element conduction matrix in heat transfer, or element conductance matrix. So this is our element conductance matrix. This is always what we want. This is the very important formula. Times temperature vector is equal to F. Now, this we don't have any difficulty. This is B transpose. We can, whatever type of element we use, this is our B matrix. Material properties go here. Another B matrix here. These are shape functions. But remember, look at this, pay attention. This term consists of everything in this bracket. Consists of two terms, this one and this. This one is for conduction. So this is actually contribution of conduction. This one, you see there is H here. This one, contribution of convection. Now, let's look at these three terms here. These three terms, F sub Q, it is this one. Remember, we said this one, N transpose Q dV, N transpose Q dV. What happens to this? Just an F lowercase q, this is this term. N transpose Q ds, and F sub H is this one. Now let's see what happens to these terms to summarize. This one now, let's apply it to one-dimensional problems. We can apply it to 2D, we can apply it to 3D, but this formula is very important. It is the result of our variational method of formulation of heat transfer problems. We can apply it to 1D, 2D, 3D. Now let's apply it to 1D. Simple case, these two will add up to give K. This is this one for 1D. This is our K. Plug the values here. For B transpose. Remember, B is this one. Transpose of this is this, B transpose. D material matrix for one-dimensional problem, it is K, conduction heat transfer coefficient, and this is B. dV for one-dimensional problem, it is AdX, cross-sectional area of the element times dx. This one, shape functions, N, this is N transpose. H is constant, comes out. Now, ds is the surface that convection is taking place, which is perimeter times dx, perimeter of the element. It's like a bar with any cross section. This is perimeter of that cross section. So just integrating, simple integration. This is just everything is constant here actually. This is dx. So integrating this k for one-dimensional problems, it is given by this. It is ak over L1 minus 1 minus 1, 1 plus HPL over 6, 2, 1, 1, 2. This is our element conduction matrix. This is contribution of conduction. This is contribution of convection. This is perimeter of that. So this I have written in this is in red too. This is very important. From the one-dimensional problem, element stiffness matrix is this. Now let's see what happens to this heat flow vectors, F. This F sub capital Q, lowercase q, and H. It is here. F capital Q is N transpose Q dV. Q is heat per unit volume. It's like body forces in solid mechanics, force per unit volume. Times volume, it is heat. Times shape function, it is F sub Q. Plug the number values, these are shape functions, 1 minus x over L for this, dx. Integrating, simple integration with respect to x, it is QAL over 2, 1, 1. The same thing, similar to this one, F lowercase q, this is this one. F lowercase q is N transpose Q ds. This is this one, N transpose Q ds. This is heat conducted per unit area times area, it is heat, and shape function, it is the heat flow vector for due to conduction from the surface. This one is from the surface of the element, so it would be perimeter times dx integrate through the length of this element. These are shape functions, and so we have x here and x here. Simple integration, we get QPL over 2, 1, 1. And very similar to this one, this last term here is this term. N transpose HT infinity, HT infinity N transpose. Just put the value. ds again is surface where convection is taking place. It is perimeter times dx. Shape functions here, this is shape functions. Simple integration of this one here, this. Now, adding these three together, we get this one. Adding this, it is QA L over 2, QA L over 2 plus this QPL over 2, and this one times 1, 1. So what does this mean? Now, this is heat per unit volume. AL is what? Cross-sectional area times length. It is volume. So heat per unit volume times volume is total heat. Half goes to each of these nodes. This one is due to heat conducted from the surface. This is heat flux. This is heat per unit area. PL is what? This is perimeter times length. This is area, surface area, times heat per unit area. This is heat. Half goes to each node. This one, due to convection from the surface. PL is area, perimeter times length is area of the element. Half goes to each of these two. All right, that was the total complete formulation that we wanted to do. The general form, remember, KT is equal to F. K is global conductance matrix, temperature vector, and force vector. All right, with this, that is the conclusion. KT is equal to F. This is the general for transfer problems. Here, I added something for radiation for those interested to see what happens in this term. So far, we talked about conduction, we talked about convection. We didn't talk about radiation. If you are interested in radiation, you can look at this. I do not, since it is not in our textbook and it's not a topic of this class, we will not. But if you want to see how we incorporate radiation also, because modes of heat transfer are conduction, convection, and radiation. If you want to see what happens to radiation, this is the formula for radiation, but it's to power 4. It is unlike it's not linear, so we have to do interpolation. I briefly wrote it here, but it's not the subject of this class. If you want to know more about this, you can ask me later, but it's not, you don't need to review this. Applying this to an example problem is the best to do this. I will briefly look at what this problem is. Since we don't have time to complete this, we will not complete this. It's not a very lengthy, but nevertheless, we just look at this briefly. This is a wall, actually, a composite wall, idealized by one-dimensional heat transfer problem. This is insulated, the wall is insulated from the outside, and it has 3 materials with 3 different, for element 1, conduction heat transfer coefficient is 5 watts per meter degree centigrade for this one. For element 2, it is 10 watts meter per degree centigrade. And for element 3, it is material properties are given here. Now, the left end is at 100 degrees centigrade. The right end is at 500. So this side 100, this side is 500. This is the cross section of this one. It is 0.1 meter square is the cross section here, and it is insulated. So this is insulated. There would be no conduction or convection from the surface. When it is insulated, there is no conduction or convection taking place from the surface of this. So whatever it is, it's just conducted. It is just conducted through the material, solid material itself, but no convection or conduction from the surface. No convection from the surface. To do this one, we model it like this one. There are 3 elements here, node 1, 2, 3, 4. This is what we derived to the element stiffness matrix. In general, it is given by this, AK over L1. This is this one, very important formula. This one for one-dimensional problem. This is the element stiffness matrix. This is this one. This is due to conduction. But this one is due to convection from the surface. You see H here. This is due to convection from the surface. But it is insulated here, so this term would be 0. This term would be 0. It is due to convection, but it is 0 because there is no convection. It is insulated. So we have to apply just this first term for these elements. This is what you see here for element 1, the same thing for element 2 and 3, and create the global stiffness matrix, set up the system of equations, apply the boundary conditions. These are non-homogeneous boundary conditions, and then we find the temperatures. Since we are over time, I do not, we will look at this in more detail, of course, on Monday next week. So, but it was to give you a heads up. I stop here, just briefly reviewing. Next week is the project due. Make sure that you submit your work on project, your project on Canvas, either on Monday or Tuesday, but absolutely no later than Wednesday by noon. Canvas closes the project next week. Do it on Monday or Tuesday next week. And the following week, the week after that, which is 2 weeks from now, we will have our final exam for this class. 10 or 15 questions, multiple choice, similar format that what we had for our quiz today. It will be accumulated. We will discuss this more on Monday next week. But 2 weeks from now, we have our final exam and we finish with this class. All right. Any questions, anyone?
Yeah, I have a question.
Yes.
How much time are you giving us for the final exam again?
I do not know. We will discuss this later. Timing, I do not. It would be 10 or 15 questions. So I do not know. We will discuss this more next week. I have not made the test yet.
Okay.
All right. Any other questions? All right. Then I stop here. Have a good rest of the day, everyone. I will see all of you on Monday next week. Take care.
Thanks, Professor.
All right.